presentation is already done. So we can go to the next presenter. This is Sylvia Putri Utami. Yes, she is a PhD student in the University of Tsukuba, Biomaterial Chemistry Laboratory, Graduate School of Life and Environmental Science in University of Tsukuba. Actually, we have still more 3 minutes for starting the next session. Already, Mrs. Putri.
Okay, thank you, Mr. Chairperson.
Okay. If you ready, we can start now.
Okay, thank you, Mr. Chairperson. First, let me introduce myself. My name is Sylvia Putri Utami. I'm a student of University of Tsukuba under supervision of Professor Hiroshi Oi and Akiko Nakagawa Izumi Sensei. Okay, today I would like to present our research, which entitled Effect of Soluble Anthraquinone Application on Prehydrolysis Soda and Craft Cooking on Acacia crassicarpa berefinery. As we know, lignocellulosic material is a common material to produce dissolving pulp. What is dissolving pulp? Dissolving pulp is a high-grade cellulose, which is an essential material for textile, rayon, cellulose ester, and others. It can be generated from hardwood and non-wood material. One of the interesting hardwood is Acacia crassicarpa because it has a good growth rate and also good wood basic density as well as acceptable yield per unit area. Crassicarpa predominantly grows in Australia and Southeast Asian countries such as Indonesia and Malaysia. Crassicarpa was known as one of the three which being tolerant to high soil temperature and soil drought, where disease conditions are the characteristic of peatland area. On the other hand, Indonesia also has more than 10 million hectare peatland area. One of the largest peatland area is in Riau province. Therefore, Crassicarpa was chosen for this study. In this figure, we see that this is a Crassicarpa plantation in Riau province, and this is also show that the Crassicarpa grows well in peatland area. To produce dissolving pulp, there are two common methods. First one is the craft cooking, which utilize white liquor as active chemical in cooking process. And the second one is soda, which only using sodium hydroxide as active chemical. And over the years, researchers try to find an interesting agent to increasing the yield and lower the kappa number. Then it found out that anthraquinone is a very good reactive agent. Anthraquinone can be synthesized from phthalic anhydride and also benzene by using aluminum trichloride as a catalyst. And it's called a Friedel-Crafts reaction. And the second one is Diels-Alder reaction. In this process, we need to react the naphthaquinone and 1,3-butadiene to produce anthraquinone. This is causing that the anthraquinone has the ability to oxidize the carbohydrate and in the same way also stabilize the carbohydrate. And anthraquinone also have the ability to reduce the lignin, and in that way they're able to reduce the lignin content inside the pulp. In general, anthraquinone have the ability to accelerate the pulp reaction and also maintain the pulp yield. On that way, it's able to reduce the cost production and also improve the environmental condition. In order to mix well the biomass and anthraquinone, it can be mixed with the glucose and also alkali, as it called a soluble anthraquinone. The next process is a bleaching sequence. There are several techniques of bleaching has been carried out in the industry, and one of the common one is elemental chlorine-free. And in order to enhance the brightness, we can use the peroxymonosulfuric acid or MPS, which has emerged as an alternative agent to enhance the brightness of the pulp from the HEF perspective. So this research aim to evaluate the effect of SAQ in Crassicarpa and also to increase the pulp yield and preserve the viscosity in a reasonable range. By employing the MPS in the bleaching sequence, it is able to increase the brightness, and also we are using bamboo as a comparison in this process. We go for the method. For the material, we are using Acacia crassicarpa, which harvests in Rio province from Indonesia, and also 2-year-old Moso bamboo from Japan as a comparison. And we are using a soluble anthraquinone and peroxymonosulfuric acid or MPS, we synthesize from dropping 98% of sulfuric acid into 60% of hydrogen peroxide at 70 degrees Celsius. Then we conduct for the next process. For the procedure, it consists 3 stages. First one is pre-hydrolysis, and the second one cooking process, and the third one is bleaching process. For the pre-hydrolysis process, we mix the wood chip and distilled water in a ratio of 5 milliliter per gram and heat for 3 hours at 150 degrees Celsius. It generates hydrolyzed and also pre-hydrolyzed wood. For the pre-hydrolyzed wood, we cook with the soda and soda anthraquinone and craft SAQ. It cooked for 3 hours at 160 degrees Celsius. It produces black liquor as a byproduct and also pulp as a main product. And for the pulp, we conducted the bleaching process, which consists of 4 stages. The first stage is the oxygen bleaching, where the pulp consistency is 30% with the pressure 0.5 megapascal and sodium hydroxide dosage 1% for 60 minutes at 120 degrees Celsius. Then afterwards, we did the D0 and modified with MPS, where the pulp consistency is 10% and the kappa factor 0.26 and the MPS dosage is 0.1% for 40 minutes at 80 degrees Celsius. And then after we conduct the alkaline peroxide with pulp consistency 10%, where the hydrogen peroxide dosage 0.42% and sodium hydroxide 0.9% for 70 minutes at 90 degrees Celsius. And the last stage is D1. We use chlorine dioxide for 0.4 to 0.6% at 70 degrees Celsius for 100 minutes. And for the analysis, we are using the TAPPI test method for the kappa number, acid and soluble lignin, S content, and viscosity. And for carbohydrate analysis for wood and pulp, we are using ion chromatograph Dionex. And for the acid soluble lignin, we are using UV spectrophotometry. And for the pulp brightness, we are using Tokyo Densoku. And for the extractive, it was determined by using acetone extraction for 8 hours. And we go for the result and discussion. In this figure 2, we see this is the relation between the kappa number and pulp yield. In the black field legend, this is show the soda and craft cooking result. And after we employ the SAQ, we can see there is a significant pulp yield, and also it able to decrease it's able to decrease the kappa number lower than without SAQ process. In here, we see that soda SAQ cooking show the similar tendency of the delignification selectivity to the craft SAQ. In this process, it also described that soda SAQ cooking has a higher pulp yield than craft, as for instance, at 23 active alkaline SAQ, it has 41.8% pulp yield with kappa number 10.4. This is better than the craft, which only have 4% pulp yield and a 10.7 kappa number. Therefore, we can see here that soda SAQ cooking is better than a craft cooking. As a comparison, we are using bamboo, which enriched with the xylan. In here, even though we are using the same active alkali, it shows that the pulp yield for the bamboo is so lower compared to the classic carpa. And the figures 3, we can see this is the relation between the brightness and viscosity, that for every stage it showed the increasing brightness, and the final brightness it has 86.7% ISO, and for the viscosity it's decreasing for every stage, and the final one is 7.8%, and it shows that this is a good, quite good result for the dissolving pulp product. Then we goes for the figure 4. In this figure, we saw the chemical components balance on pre-hydrolysis soda SAQ cooking of acacia and bamboo. In the raw material, we saw that the classic carpa has contained a high glucan and xylan. Even though in this raw material, we saw that bamboo has more xylan compared to the acacia. And after the pre-hydrolysis, it's able to remove the xylan into the hydrolyzed liquor. For the acacia, for about 4.7%, and for the bamboo is 1.9%. And after the process for the cooking, we found out that the lignin content inside the pulp, in the unbleached pulp, the lignin are only 2%. It means the pre-hydrolysis and soda SAQ cooking able to decrease the lignin. In other way, also maintain the glucan content inside the unbleached pulp. And after the bleaching sequence, we can see that the pulp yield process is not really different. It's able to maintain the pulp yield. The pulp yield loss not really different enough. Okay, in the other way, we see that the hydrolyzed from the pre-hydrolysis can be proceed into the furfural production for the biorefinery, and for the black liquor, it can be purified into the lignin isolation. Then we can jump into our conclusion that the effect of soluble anthraquinone on the pre-hydrolysis soda cooking and also by modifying the ECF bleaching were clarified. The using of classic carpa was proven has the potential for the dissolving pulp, and the pre-hydrolysis soda SAQ cooking of the classic carpa provide a significant improvement in the increment of pulp yield and able to decrease lignin content than a craft cooking. The modified ECF bleaching should be success to obtain a high brightness and viscosity around 7 centipoise. This process offers an environmental advantage while achieving the good range of brightness and viscosity for the final bleach up. Okay, thank you everyone for your kind attention. Thank you. I give it back to the chairperson.
Thank you very much for the presentation, Mrs. Putri. Now open for the question and discussion from the participant. Is there any question? If there is no question, I would like to confirm the one thing. What is your justification of comparison between Acacia crassicata and Osu bamboo in your result? Why you add the bamboo result in your research?
Thank you, Mr. Agusta-san. We know that bamboo has a high xylene and also has the potential to generate the dissolving pulp because it has a good, also it has a high glucan content inside the bamboo. And actually we want to see the ability to remove the xylene inside the bamboo by using the same procedure that we apply for the crassicarpa. It's soon out that the xylene content inside the bamboo still not removable well. So this is the next project that we need to concern about. So this is we just want to apply the procedure in the same way. So it turned out that it's still not working well. I think that's Thank
you very much. We have a question, I think, from Indonesia, Mr. Andri. Would you like to ask the question by yourself, Mr. Andri? Mr. Andri. Please.
Yes. So my question is that you stated that MPS might decrease the chlor dioxide or maybe chlor dosage. However, you didn't show it on your data that chlor was decreased. So maybe you could explain how this is happened, because you didn't also you didn't compare it to ODED. I mean, without the MPS. Thank you.
Yeah, thank you. In my study, I still not yet compare this bleaching sequence with and without the MPS. As I can say that by using the MPS, actually, because I compare with another researcher that they're not using the MPS, the chlorine dosage that they use is more than the one that I use in this process. That's why I can clearly say that by employ the MPS, it slightly decrease the chlorine dosage that we use for the bleaching sequence. Actually, Mr. Agusta-san will present this kind of about the MPS of beneficial tomorrow. Maybe you can also join with the presentation tomorrow to hear.
Okay, thank you. I will ask Mr. Agusta later then.
Thank you very much, Mr. Andri. Okay, please tomorrow still join with us. Okay, any other question? We still have time. If no, I just want to confirm about your slide in the result. Could you show the results slide? We still have around 4 minutes. So in the slide 12, yes, this is to compare some of the active alkali. 12, please. in here you compare some active alkali dosage, different cooking method also, and one using SAQ and not using SAQ.
Yes.
Could you point out some point that clarify the effect of the utilization of the SAQ in here?
Okay, thank you, Agustosa. In this figure 2, we see that the fill black legend is without the result for the cooking without SAQ. In here, we see that even though this has a higher pulp yield, it has a quite high pulp yield, and but it also has the low high kappa number. But as example, for 20%, actually, for the 20%, after we employ the SAQ, we can see there is a significant kappa number difference. The kappa number become more lower for the 20% of the active alkaline dosage compared to the result without SAQ. So after we employ the SAQ, the kappa number become decrease a lot, significantly and also it still maintain the good pulp yield. And in this one, we believe that the soda SAQ cooking has a good process for the cooking process. I think, yeah. As also I mentioned that for the instant, for the soda SAQ, it has for the 23% for the soda, it show it has a high pulp yield 41.8% with the kappa number very low is 10%.
Okay, thank you very much for the clear answer. I just want to inform that after this presentation by Mrs. Putri, we will have the coffee break until 3:25 Japanese time. 3:25 Japanese time. We will have coffee break, and next session will be held by Professor Shiho Takahashi from FFPRI. So please don't forget to join us again in 3:25 Japanese time. Thank you very much. I will give back to the chairman, Professor Oi. Thank you very much.